Hello, my name is Leonid Chekhanovsky, and this my channel Brave Stories. Today, we are going to talk about what may be one of the most revealing technical stories of the war. The real state of Russia's so-called new R-26 Oreshnik missile. Not from propaganda, not from official statements, but from the physical debris collected after the strike in the Lviv region. According to available reports, the missile was launched from the Kapustin Yar test range, roughly 1,600 kilometers from western Ukraine. It struck infrastructure targets in the region. Fortunately, there were no casualties and the material damage was limited. Within 24 hours, Ukrainian specialists collected large amounts of missile debris scattered over a wide area. This detail is important. The fragments were spread across more than a kilometer, which strongly suggests that the missile broke apart in the upper atmosphere during re-entry. Many people assume the greatest stress on a missile happens during launch. In reality, the most extreme loads occur when the missile re-enters the dense layers of the atmosphere at hypersonic speed. At that moment, structural loads can reach 50 to 80 grams. If the structure is not strong or stable enough, it simply cannot survive those conditions. And that seems to be exactly what happened here. Let's now move to the most interesting part, what was actually found inside the debris. Engineers who examined the fragments immediately noticed something unusual. The internal electronics looked extremely outdated, even by late 20th century standards. The first thing that stood out was the wiring. There were large bundles of cables connecting different circuit boards. In modern systems, high levels of miniaturization allow many functions to be integrated onto a single board or even a single chip. Here, instead, multiple boards were connected with large quantities of wires. Even more surprising was the type of wire used. Specialists identified it as a vinyl-insulated aviation wire design that traces back to American aircraft of World War II. The Soviet Union copied this standard decades ago, and it has continued to be used in certain legacy systems ever since. The cable bundles were wrapped in cloth tape and secured with electrical tape, methods more typical of mid-20th century equipment. By modern aerospace standards, this is considered obsolete and unreliable. Next, analysts found large circular connectors known as SHR-type connectors. These were commonly used in Soviet equipment in the 1960s and 1970s. They are bulky, heavy, and not suitable for modern compact electronics. Today, most advanced systems use much smaller, lighter, and more robust connectors. Another key discovery was a mechanical gyroscope. This is a major indicator of technological age. Modern missiles typically use ring laser gyros or fiber optic gyros or advanced MEMS-based inertial sensors. These are compact, solid-state devices with very low drift and high reliability. A mechanical gyroscope, by contrast, is an older technology. It requires electric motors to spin up the rotor before launch. It accumulates navigation error over time and is more sensitive to shock and vibration. Finding such a device inside a supposedly modern missile raises serious questions about the level of technological modernization. Investigators also reported very large resistors and capacitors, similar in size to components used decades ago. Some integrated circuits appeared to be Soviet-era designs, with large packages and relatively low integration density. In one fragment, a component carried a manufacturing date from 2018. This is interesting because the R-26 Oreshnik was reportedly assembled or modernized much later. The presence of older components suggests that parts from existing stockpiles were used rather than newly developed electronics. So why does a missile presented as a modern system contain such outdated technology? The likely explanation lies in how the R-26 Oreshnik was developed. Reports indicate that the missile is assembled at the Votkinsk plant, where Russia produces the R-24 Yars intercontinental ballistic missile. Instead of designing a completely new medium-range missile from scratch, engineers appear to have adapted existing hardware. The concept is relatively simple. Take a 3-stage intercontinental missile, remove one stage, and you get a shorter-range system. With 3 stages, the Yars can reach intercontinental distances. With 2 stages, the range drops into the medium-range category, roughly a few thousand kilometers. But there is a catch. Missile systems are extremely sensitive to design changes. Even small modifications to electronics or structural components usually require extensive testing. This can mean dozens of test launches before the system is certified. To avoid long development cycles, it appears that engineers kept as many original components as possible. That means older guidance systems, older wiring standards, and older electronic modules. In other words, instead of building a new missile with modern electronics, the designers likely reused proven but outdated components from earlier systems. This also explains why the internal architecture looks closer to Cold War technology than to contemporary aerospace standards. Another important factor is production capacity. The Votkinsk plant is reported to produce only a limited number of large missiles each year. If that capacity is shared between intercontinental missiles and medium-range variants, the total number of new systems produced annually would remain relatively small. Now, let's summarize the key technical observations from the debris. Key findings from the Oreshnik debris. Extensive use of large wire bundles instead of integrated electronics. Vinyl insulated aviation wire designs dating back to mid-20th century standards. Cloth tape and electrical tape used for cable harnessing. Large SHR-type connectors, typical of 1960s to 1970s equipment. Mechanical gyroscope instead of modern solid-state inertial sensors. Oversized resistors and capacitors. Integrated circuits with low density and older packaging. Components manufactured years before the reported missile assembly date. All of these indicators point in the same direction. The internal electronics appear to rely heavily on legacy technology. This does not automatically mean the missile is ineffective. Older technology can still function, especially if it is robust and well-tested. However, it suggests that the system may not represent a true technological breakthrough, but rather an adaptation of existing designs. And the fact that the missile appears to have broken apart during atmospheric re-entry only adds to those concerns. In modern missile design, structural integrity during re-entry is one of the most critical challenges. If the system cannot survive that phase reliably, its practical effectiveness becomes questionable. The debris analysis gives us a rare physical glimpse inside a system that is usually surrounded by secrecy and propaganda. And sometimes, fragments of metal and wires can tell a more honest story than official statements. What do you think about these findings? Do they change your perception of the Oreshnik missile and its capabilities? Subscribe to the channel, leave a like, and share your thoughts in the comments below.